Okay, so today I thought that we would continue on with our discussion of two-dimensional linear drag. In other words, we're going to look at linear drag, so having a drag force that's proportional to the velocity to the first power. But now, instead of looking at just one-dimensional vertical motion, let's look at two-dimensional projectile motion. So here are our equations of motion. We've got our net force, so mass times acceleration, will be two terms. The gravitational force straight down at all times, of course. And then we'll have this drag force that, notice, is minus the direction of the velocity vector, and it's proportional to it. Sometimes people will call this like b or something. I decided to factor out a factor of m just to make the math a little easier later on. So I'll call this gamma, the drag coefficient. We have two goals today, and this is kind of based on problem 3.53 of Morin's classical mechanics textbook. First thing I want to do is I want to determine all of these things. I want to know what is the position as a function of time, so the parametric representation of the trajectory. I want to know the velocity as a function of time, both components, and I want to know the acceleration as a function of time, both components. Then we'll look at sort of a special case where if the initial drag force, so this is the drag force magnitude at time zero, happens to be exactly equal to its weight, then what is the angle that would maximize my horizontal position for the apex of the trajectory? This is not quite as hard as finding the range. We'll maybe do that in a different video, but the question is, how would I maximize the x-coordinate of my vertex? What angle of launch would give me that? And as usual, we're assuming that we're launching with some initial speed v naught, and we're launching at some initial angle theta. Okay, so the first thing we want to do is solve this differential equation. So I'll start by rewriting it, canceling all the m's. And actually, I'm going to go ahead and write out the components separately. Okay, so those are our two differential equations for the y and x components of the velocity. Notice that they don't mix each other up, so they're independent, and they're linear, they're nice. We can easily separate variables or even use integrating factors depending on what you're more comfortable with. We actually have done this one before, but just as practice, let's do it one more time. This first one, I'll quickly show what the result will be from separation of variables. Okay, so going through that separation, integrating both sides, and then remembering our initial and final conditions, we end up with this logarithm. So solving for Vx of t, I'll just put it right up here. So we see that the x component of the velocity just exponentially decays with time from its initial value. Okay, now let's do the second equation. And maybe this one, let's use an integrating factor just to mix it up. So here, notice that this is of the form dv dt plus gamma v equals a constant. So that's kind of our standard form where this coefficient of the linear term is a function. It's a constant function, just gamma. And our integrating factor, mu, is usually found as the exponential of the integral of this prefactor function. So if I multiply both sides of my equation by this integrating factor, the left-hand side will become basically a differentiation by parts, or I should say a product rule. So we can combine them back together and then integrate both sides. So as I said, this part was exactly chosen so that this all becomes, I'll let you go ahead and do the product rule on this to see, yep, it expands back out to these two pieces. And then the right-hand side is just some new function of t. Now I can just integrate both sides of this with respect to t and get my final result. Let me bring that up and we'll finish off one more bit of math here. Okay, so this is after integrating both sides from 0 to t, plugging in these values here. Obviously, e to the 0 is just 1. And then on this one, we pick up our usual 1 over gamma from this antiderivative. Plugging in t, of course, gives me the t, and then plugging in 0 does give me an e to the 0, which is another 1. And then simply solving for vy of t will give me my final answer, which I'll put up here. Okay, so here are my two solutions. We have our x component for the velocity and our y component for the velocity as functions of time. Of course, we actually know our initial conditions, which are, maybe I'll write over here. V naught cosine theta, V naught sine theta. So plugging these in here will give us our velocities as functions of time in terms of these parameters and our initial conditions. So we found our v of t. Let's go ahead and take the derivatives to quickly find the accelerations as a function of time. So my x acceleration, taking this derivative, will just give me, well, so we do see that the acceleration is negative, which it should be. The drag force is basically going to decelerate in the x direction. Some component of it. It does decay exponentially with time as well. And then when we take our vertical acceleration, I actually don't really need to do any extra derivatives here because it comes directly from Newton's second law. I could just go ahead and write down, oh, it's going to be some sort of negative g and then minus this component of the velocity, which we have just found. But of course, we could also take the derivative to find it. So we have these two pieces. This constant term will have 0 derivative, and then these two pieces will each give some exponentials. That's this first piece. And then the second piece will have a minus. Minus becomes a plus. And then when I bring that derivative down, I get another minus gamma. It actually multiplies by this, so I'll just go ahead and call that g. And we're still left with this exponential decay. And we could, if we want, group those together to factor out that common decaying exponential. Okay, now that we've gotten our accelerations and our velocities, let's go ahead and finish this off with one more integration to find the components of the position. So first, let's go ahead and do the x component. So here is our velocity equation as a function of time, which we know is the rate of change of the x coordinate. We're just going to integrate both sides, real easy. On this side, we'll just have x. Of course, that'll be x minus x naught, but let's assume we start from the origin. And then, of course, we have to integrate this. Don't forget that our lower bound of 0 will not be trivial here. We'll have to plug that in. Okay, so there's our antiderivative. And then when we plug in t, of course, this is the same function. Plugging in 0 does give us a e to the 0, which is 1. Since I'm subtracting them, I'll go ahead and wrap that negative sign up with flipping those two bounds. Sorry, that should be a 1 over gamma. Okay, so here is our x position as a function of time. We can always, of course, check that the dimensions make sense. So notice that the dimensions of gamma, since gamma times v is supposed to be an acceleration, then the dimensions of gamma are 1 over time. Of course, we can also see that from the argument of this transcendental function. And sure enough, velocity divided by 1 over time does give position, so that's good. We can also check to see that something interesting happens here. As t goes to infinity, this term goes to 0, which means my x-coordinate approaches asymptotically some sort of, I don't know what we want to call it, a vertical asymptote. It never actually gets farther than v naught over gamma cos theta. And if we're thinking about the trajectory, what the shape of this looks like, and we'll probably analytically do this in a future video, we're launching this thing from the origin, but drag is going to make it turn over. So this initial launch angle is, of course, theta, and we've got some initial launch velocity, v naught. But we've just found that as time goes to infinity, obviously it'll probably hit the ground first, but if there was no ground here, if this is a big, 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 big hole, eventually over here there is some kind of vertical asymptote where if this thing were allowed to continue, it would sort of asymptotically approach that. We'll see what y looks like in just a sec. And this location is sometimes called an aerodynamic wall, meaning if you have drag, whether linear or quadratic, we'll see this for a quadratic case too, there will be some maximal distance horizontally that you can go, no matter how hard you launch it, no matter what angle that you launch it at. I mean, obviously it'll depend on both of those conditions, but there's no way to go arbitrarily far for a fixed launch speed and fixed launch angle. So this aerodynamic wall is kind of a hard stop on letting projectiles go sort of arbitrarily far. Okay, so there's our x component. Now let's put up our y component of the velocity and integrate that. Okay, so I've written it back up here. I did go ahead and regroup things a little bit so that the time dependence is attached to this one constant, and then our time independent piece is on its own. Just makes the integration a little bit easier. And now we'll integrate both sides. So again, same sort of deal. We're launching from y equals 0, so this side will simply be y. And then when we integrate this piece and this piece separately, this piece will be a minus 1 over gamma from doing our sort of inverse chain rule. And then this piece right here will just pick up a t. Okay, once again, we can't be too cavalier about just dropping this lower bound here. Here it didn't matter because t equals 0 doesn't give us anything. But here we do pick up that 1. And just like before, I'm going to go ahead and get rid of this negative sign by swapping my bounds of integration here. So I'm going to have a 1 minus this exponential. Okay, so this one is also a little bit interesting as far as the behavior. Notice that as t gets very, 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 very large, this exponential term goes away. We're left with more or less a constant. So there's this curious overall positive constant that's sort of there. Of course, this term will get more and more negative as expected. And we do kind of think that, yeah, even if there's drag, we should continually have the y position get lower and lower as it falls due to the influence of gravity. The thing that does happen is if we go back up here, when t goes to infinity for the velocity, this whole first term goes to 0, and we're left with this overall negative g over gamma. But of course, that piece right here is the terminal velocity. So we do expect this thing to basically end up going straight down at a constant speed far, far in the future. And if you're moving at roughly a constant speed, then of course your position will be changing linearly with time. That's not too surprising. Okay, so we have everything together. I didn't have room to put them all on one board, but we do have the velocity components as a function of time, the acceleration components as a function of time, and the positions as a function of time. In a future video, we'll go ahead and eliminate time from my x and y components to get a trajectory equation, so it can kind of plot what this actual graph is. It'll look kind of like a parabola, but you already kind of saw it's got this asymptote. And maybe we'll also look at the limit where gamma, this drag coefficient, goes to 0. You might notice that if you try to take the limit as gamma goes to 0 naively here, kind of looks like we're dividing by 0 in a few places. Might have to worry about that. Obviously, the result we should get is our usual classic no drag parabola, but we'll have to check it more carefully. Okay, so let's clear this up, and then let's go ahead and look at answering this second question. Okay, so I have gone ahead and rewritten our position components and our velocity components as functions of t, just so we have them for reference. And now we're going to look at this specific case where the initial drag force is equal to the weight. That's going to put some conditions on V naught, gamma, and G. In fact, notice that the initial drag force magnitude will just be m gamma V naught. And if we set that equal to mg, we see that we're in the unusual situation where our initial velocity just so happens to be the terminal speed. Okay, that'll just make our life a little easier. Now, when y is at its maximum, so when we're at the highest point in the trajectory, we know that the y component of the velocity will be 0. So if I go ahead and sub this in for v naught here and do a little bit of factoring, we'll go ahead and solve for that e to the minus gamma t term. Oh, and I just realized there's a little bit of a typo there. This one doesn't have a t. It only showed up here. Okay. So plugging that in here, we end up with 1 plus sine theta. I'm going to factor out the g over gamma from both those terms using this v naught. And I'll even go ahead and factor it out of this as well. So there'll be a 1 plus sine theta e to the minus gamma t minus 1. All of this will be times g over gamma. And I want to set this equal to 0 because that will tell me that location, or at least the time, when we reach that maximal location, maximal height. Okay, g over gamma is not 0, so that means I can solve for the time at which this occurs. And I'm actually not going to solve for all of it. I just want this exponential piece to plug back in here. And that will be what? 1 over 1 plus sine theta. So that's finding kind of the time at which the y component is at its maximum value. Now I'll plug this back in here where I've got my x of t. So the x value at this maximal point. And I will go ahead and replace my v naught. 1 minus this exponential. And we could do a little bit of trig simplification here, finding a common denominator and then combining. So the common denominator will be 1 plus sine theta. 1 plus sine theta minus 1 will just be sine theta, and then I have a cosine as well. Okay, so this is the x-coordinate of my peak in this special case of my initial velocity being my terminal speed. Now I want to maximize this with respect to theta. So let's bring this up and we'll take our derivative. So notice that actually when we take this derivative, it is going to be a quotient rule with these angles. So we'll go ahead and do that. Okay, quotient rule, bottom times the derivative of the top. You might say, well, you could do some trig identity to make this a half of sine 2 theta. Yeah, we could, but honestly, I want to keep things as a polynomial in sine theta at the end, so I'm going to leave it. That means the derivative here will be a product rule. So I'll have a negative sine squared theta from sine times negative times the derivative of cosine, which is negative sine. And a cosine squared theta from cosine times derivative of sine. And then we'll need to multiply by the derivative of the bottom, which is just cosine. Okay, almost went off the board there. All of this is divided by the denominator squared. But since we're setting this to 0, and I'm not so concerned with the case of theta being like negative pi over 2, or, I don't know, shooting down into the ground, we don't really worry about that. I want the numerator to be set to 0. What I'm going to do is I'm going to replace these cosine squareds here and here with 1 minus sine squareds to get a polynomial in sine theta. Okay, so I'm going to set this numerator equal to 0. Remember, I'm going to replace this cosine squared with 1 minus sine squared. So that 1 and this 1 will give me a 1. I'll pick up a negative 2 sine squared theta. Then I'll also pick up a sine theta from the 1. And then I'll have a minus 2 sine squared times sine is minus 2 sine cubed theta. And then my last bit here, cosine squared will be 1 minus sine squared, which I distribute with this sine. So I'll have a minus sine theta and then a plus sine cubed theta. All right, let's try to make this look a little prettier. The sine cubes can combine and give me a negative. I'll just clear all the negatives here. So I'll have 1 positive sine cubed after I reverse the negatives here. My sine squared doesn't have anything to combine with, so that'll just become a positive 2. I have a sine theta minus a sine theta. Well, those cancel out. And then I'll have a plus 1, which becomes a minus 1. Okay, now this is a cubic equation, and those might be a little scary, but actually this one factors kind of nicely. There's a couple ways of seeing that. You could kind of use like a rational root theorem approach. As a reminder of what that is, since my leading coefficient and my constant are both plus or minus 1, the only possible rational roots would be plus or minus 1. And you can go check with either synthetic division or polynomial long division that negative 1 is a root here. So if I do sine theta plus 1, that factors into this pretty nicely. And what will we left with? We'll be left with a sine squared. The constant term will have to be a minus 1. And then for the sine theta coefficient, what will we need? Let's see, I'm going to need a sine squared from this and a sine squared from this adding to a 2. So that's actually pretty easy. Now this whole thing is set equal to 0. So this one's a little weird. Sine theta is equal to negative 1 when theta is like minus pi over 2 or maybe 3 pi over 2. That's like firing it straight into the ground, which it does give you an extremum of x. It just gives you a minimum of 0, so that's not interesting to us. This second bit is a little more interesting, and you'll notice that we are going to have to use the quadratic formula to find our values of theta that satisfy that. So let's quickly use that up at the top of the next bit. Okay, so here's our quadratic formula. Negative b plus or minus b squared minus 4ac. Notice the interior of the radical will give you a 5, so I'll have root 5. And then I'll have a negative 1 plus or minus root 5 over 2. Now, we don't really want the negative sign here for both of these because then sine theta would be negative. And again, I'm kind of launching into the ground. That's also a minimum. I don't want that. But if I use the positive sign, I get something that actually is a positive number. And this is actually equal to the golden ratio minus 1. Or said another way, it's the inverse of the golden ratio, which is kind of interesting. That tells us that the angle that sort of maximizes this horizontal position of the apex of this trajectory is the inverse sine of the inverse of the golden ratio, which turns out to be approximately 38.2 degrees. It's nice to see an old friend. The golden ratio shows up in almost every problem if you look hard enough. So we've done it. We found our position, velocity, and acceleration components for this 2D linear drag problem, at least parametrically. And in this special case where the initial velocity happens to equal the terminal speed, we found that to maximize the horizontal position of the apex, you should launch it at this curious angle. QED.